Well, okay, so I'm going to start now. Good afternoon, everybody. This is the last class about exegetic analysis. We're going to talk about Gibbs free energy and chemical exergy. I think we mentioned something similar on last class, that exergy is associated with the potential to generate useful work from a difference in terms of state, the state of a substance, for instance, with respect to the environment. This difference can be in terms of pressure and temperature or chemical composition. That's what we're going to see today. I showed you last class this what we call osmotic power plant or osmotic elevator, which was run simply because of due to a difference in concentration. You have high concentration salt water, for instance, and sweet water here, and just this difference in concentration can be used to generate power. We're going to expand this concept today to, for instance, when you have chemical reaction within the system. Okay. Another broad view of this problem is our agricultural or agro-industrial model composed of a production section, okay, logistics, and industrial conversion. If you focus on the difference in terms of concentration and chemical composition between the feedstock, the agricultural feedstock, and the energy carriers, substances, and processes, of course, this energy flow, which is maintained by solar power, okay, is another example of useful energy being generated from a difference in terms of chemical composition and even reactions. Okay. When we talk about just another reminder before we get into the subject, another important aspect of this problem are chemical reactions. We're going to end this class talking about chemical reactions. This is, again, the Sankey diagram of United States energy use in 2013, okay? And if you look at where in these boxes you have important reactions, here, for instance, in converting biomass to some energy carrier, it can be electricity. I don't know if you can see the line here. This is electricity, okay? Or biomass being used as a feedstock for electricity generation. So you have combustion here, basically. And also biomass being converted to some kind of fuel, okay, to the transportation sector. And here you have, for instance, fermentation, which can be seen also as a biochemical reaction. So you have chemical reactions in many of those places. Combustion here, combustion if you use, for instance, natural gas for heating in industry. Okay, so you probably are using a combustion to generate heat. Likewise in the commercial sector and of course in the residential sector too. Okay, so chemical reactions play a very important role in this flow. I mean, I want you to see this as a kind of a flow from feedstock to energy carriers, okay, feedstocks, energy carriers, and end users, okay. Every time you have a conversion from feedstock to a specific carrier, from biomass to ethanol, for instance, you have a chemical reaction. So this conversion is the focus of our class today. Okay. Just to remind our definitions, exergy, also called available energy, exegetic energy, or availability, reversible work, and so on, okay, has a very, I would say, beautiful definition. Okay. So exergy is defined like this, what we call thermodynamic exergy. U stands for the internal energy of the substance, V its volume, and S its entropy, okay? And the index 0 refers to the property of the substance when it is in equilibrium with the environment, okay? So U0 is, let's say that X is the exergy associated with, I don't know, 1 kilogram of water, okay? So U is its internal energy, and U0 is the internal energy of water when it is at the same pressure and temperature of the environment, okay? Likewise for pressure and temperature. So an important aspect of Exergy is that it considers also the properties of the environment. Okay, so if you're analyzing, for instance, a power plant to be built, I don't know, on the equator, it will behave very differently if it's built on the South Pole, for instance, and this can be taken into account in a very straightforward manner by using Exergy. Okay, if you have other components like potential energy and kinetic energy, you simply add these terms here, okay? And if you have chemical exergy, the possibility of producing useful work from chemicals, from difference in terms of chemical composition, okay, between the substance and the environment, and you simply add this term here. What we're going to see today is how can we assess this term here, okay? Because potential energy and kinetic energy, they are 100% exergy, but this is not the case for chemical exergy, okay? So we're going to see this today. Before we go to this definition, let's see, like I would say, a similar thermodynamic property, which is the Gibbs free energy, okay? And we're going to take a closer look on chemical reactions, okay? So an entry point on this subject would be how to quantify the spontaneity of a certain process, okay? This is the key word here. We are worried about how spontaneous a given process is. Okay, it is a natural process. It occurs naturally, or you have to force it somehow. Okay, we have seen in later. Oh, sorry, I did something here. We have seen in other classes that, for instance, if you have a separation process like this one, you have a mixture of A and B, and you're separating A from B, and we already know that this process needs to import work, okay? So it absorbs exergy, it absorbs useful work, okay? This we already know. If you have a, so this is okay. If you have a chemical reactor, for instance, or a mixer, better saying like this, if you have a mixer, A and B entering separately, it's being mixed, okay, and you have A plus B, and so it's very natural. There are some, given that the energetic state of the output is lower than the input, it's natural to have some amount of energy release. If you mix alcohol with ethanol and water, okay, this mixture, when you mix, this mixing process releases heat, it releases energy. But if you have a chemical reactor, as it is depicted here, okay, A and B entering the chemical reactor, the process, and the species are changing, okay? So you have A plus B combining, reacting to give C plus D, okay? So how can we know if this process releases energy or absorbs energy? This is one point. And how can we know if this process is natural, okay? Or if you have to force it somehow. That's the point today. So we're going to focus on this process here today, okay? So let's reason in terms of a very common example. Nitrogen and oxygen, okay? Right now, in this moment, everybody's breathing roughly 71%, 79% nitrogen and 21% oxygen. That's the composition of the atmosphere, okay? And we know that at low temperature, nitrogen is not reacting, does not react with oxygen. So if you input this into a reactor, if the reactor is at low temperature, nothing is going to happen. Okay, the molecules, let me make some drawings here. One molecule of N2, okay, if it bumps into another molecule of O2, they'll bounce back simply because they don't have enough energy to react. Okay, so O2 continues to be O2 and N2 continues to be N2. Okay, this is at low temperature, meaning the speed, the velocity of these molecules are not high enough to disrupt the liaison between one nitrogen atom and another atom of nitrogen. Okay, but let's think at this case. At very high temperatures, this velocity is so high, the velocity with which nitrogen is bumping into oxygen, the velocity is so high that it disassembles the nitrogen molecule. Okay, then you may have for a fraction of a second you have one atom of nitrogen and one atom of oxygen, and they can react. Okay, so at very high temperatures you may have the formation of NO and actually NO2. Okay, so we know this happens empirically. We know this happens at high temperature. Nitrogen and oxygen starts to react, and at a medium temperature, well, you can have both. You can have I don't know, 10 molecules of nitrogen bouncing into 10 molecules of oxygen. Half may continue to be nitrogen and oxygen, and the other half may react to give NO. Okay, so I would say that at medium temperature both can happen. Okay, so that's an empirical fact. Let's try to measure, to assess how spontaneous the process is. You know that in this sense, N2 mixing with oxygen but not reacting is a spontaneous process at low temperature. Okay, and N2 and O2 reacting to give NO is a spontaneous process at high temperature. Okay, so temperature influences the spontaneity of a process, and we're going to have to take this into account. The guy who did this, who first thought about this, was obviously Gibbs, and what he wanted to do, he wanted to assess the spontaneity of a process. And the variable that he wanted to construct is something like a thermodynamic potential that vanishes when the process reaches equilibrium at constant temperature and pressure. Equilibrium would be something like this. It can go in the direct sense or in the inverse sense. Okay, so it's neutral. Okay, the sense. Okay, and well, he didn't baptize Gibbs free energy. Okay, now we used to call it like this. But it also has other names: Gibbs free energy, Gibbs function, Gibbs potential, free enthalpy, and so on. And this has nothing to do with the Bee Gees, okay? The Gibbs brother, okay? They are different people, okay? But let's take a look. Let's try to reason the same way that Gibbs did, okay? So let's consider this reaction, or N2 plus O2 in gaseous phase, okay, at a given temperature T phi, okay, given two molecules of NO, okay. When we apply first law of thermodynamics, okay, let me write it down here. First law of thermodynamics: work minus, the opposite, heat minus work, okay, so heat input minus work output equals products minus reagents. Okay, that's the first law of thermodynamics. I'm applying this to this control volume. Okay, well, we can think about this being adiabatic. There's no work being released, so the variation will simply be this sum here. Okay. So if the process is adiabatic, this is 0. If this reaction releases some amount of heat, I'm going to write it like this, heat, okay? If this is the case, so that component goes here, okay, heat. And that's what we're doing. So this equation reflects exactly this situation, when you have a certain amount of heat release. Okay. If we make all the calculations, for instance, if I look at the enthalpies of oxygen and nitrogen and nitrogen monoxide, okay, I have these numbers. Those are charted data, okay. So 2 times 9.29 kilojoules per mole that's the enthalpy of NO, okay, at 25 degrees, okay, minus 0 and 0, because 0 and 0, that's the enthalpy of nitrogen and oxygen at ambient pressure and temperature, okay. That's a convention. So you get this number, okay, plus 180.58 kilojoules. So that's the heat involved in this reaction. So you could write like this, 180.58, okay? And this means that the process absorbs energy, okay? Remember our convention, when you give heat to a system, like in Newcomen's machine, you put coal in the machine, so you're giving heat to the machine, and the machines give you back work. So heat going into the system is positive, and work going out of the system is positive. That's a convention, okay, which we're following here. So this sign plus means that the process is endothermic, okay, and where do you think this energy comes from? This means that 180 must be absorbed, okay, for this reaction to take place. Okay, and why is that? Because the energy content on the right-hand side is greater than the energy content on the left-hand side. So you need to absorb energy. Okay, let's write it like this: energy. And where do you think this energy comes from? Okay, because, well, when a reaction releases heat, it's simple. Heat simply goes away. Okay, but this energy may be coming from an external source, of course, but it may be related to the kinetic energy of the molecules that are bumping into each other. Okay, like in here, one molecule of N2 bumping into one molecule of O2, and so it may be coming from its internal energy, meaning temperature. Okay. Okay, let's move on. So remember, I'm going back some slides. I'm trying to reason here. We're trying to construct this thermodynamic potential that vanishes when the process reaches equilibrium. We're trying to build this variable. Okay, we're trying to follow Gibbs' step. Okay, so we know this reaction is endothermic. Okay, and we can formulate some conjectures. Okay, when a process is endothermic, meaning it must absorb energy from an external source or from within its components, we can assume the process is less spontaneous. Okay, if the process is exothermic, meaning it releases energy, it releases heat, so the probability of being spontaneous is higher, I would say. Okay, so in this case, more spontaneous. So what we know already, Okay, if a process releases heat, or this variable that we're trying to construct must reflect this conjecture, okay, that the process becomes more spontaneous. And in the opposite sense, if it's endothermic, the variable that we are constructing must reflect the fact that it is probably less spontaneous. Okay, so let's analyze one case. Actually, I want to analyze two cases, trying to infer how this variable could be proposed, could be defined. Okay, so in this case, okay, we're assuming that the process is exothermic, it's releasing heat. Okay, so that's one thing. Okay, and also the process, its entropy increases, meaning that the level of disorder, okay, disorder increases. And well, I think we have a pretty good idea that when the level of disorder increases, the process tends to be more spontaneous. Okay, so let's consider this case: two molecules bumping into each other. Okay, the molecule. Let me get my pointer. This one, one atom of A and two atoms of B. Okay, is bumping into another molecule C and D here. Okay, so let's try to reflect these assumptions here. Okay, so they bump into each other, they react. For instance, like this, you have B reacting with C, or connecting with C, B connecting with D, and you have a single molecule or single atom. Okay, and you have energy releases. You can imagine like those crash tests you do with cars. So those are two cars bumping into each other, and now you have, well, parts of car moving around, but the fact here is that you have more parts after the shock than you have before. Okay, you have two parts here, now you have three parts. So having three parts, or they may combine differently, this implies that the entropy is increasing. Okay, and the fact that entropy is less than zero, delta H is less than zero, means that the process is exothermic. Okay, well, so we know this. Okay, or cars just crashed into each other and spread various pieces all over the place. Okay, so in this case, it's natural to assume that the process is spontaneous in the indicated sense. Indicated sense means in this sense. Okay, two molecules bumping and bringing about three molecules. Okay, so since the process is exothermic and entropy increases, the process is spontaneous in the indicated sense at any temperature. Okay, if it's spontaneous in the indicated sense, in the opposite sense, you have smaller probability of three molecules bumping into each other at the same time to form two molecules. Okay, so the process should be non-spontaneous. Okay, it's like reversing the movie. Okay, you have parts of car bumping into each other at the same time, and they are assembling the car before the crash. Okay, so this is probably well, I wouldn't say impossible, but almost impossible. Okay, another point is that Another point is that the product's three molecules are at lower energy level compared with the reagents. Okay, this explains, or this justifies the fact that the process is exothermic. Okay, let's. It's written case 1. Well, this is a mistake. Okay, this is case 2. The process is still exothermic. Okay, it's releasing heat. let me correct this here just so we don't have a problem. In this case, the process is still exothermic, but entropy is decreasing. So the level of disorder is decreasing. So we have now two molecules, B, bumping into a molecule of A, okay, and it's forming a single molecule, ABB, okay, releases energy. So the number of parts before the reaction, before the shock, is smaller than before the, sorry, I think I said it wrong. The number of parts after the shock is smaller, 1, than the number of parts before the shock, 2 molecules, okay? So this is due to the fact that entropy decreases and exergy, energy is being released because delta H is less than 0, okay? It's like an inverse crash test. As I already said, it's like many parts of many car parts bumping into each other, and they at exactly the right place, at the right speed, okay? They don't bump and bounce back. They are at the exact right place and speed, okay? And they assemble the car. So this is, well, I would say almost not impossible, but it's very hard to happen, especially if those parts are bumping into each other at a very high speed, okay? So we could say that this process is conditionally spontaneous in the indicated direction, okay? At low temperature, well, this may happen, okay, because even though it's hard to imagine, okay, these at low temperature they are approaching at low speed, okay, so they have probably enough time to combine and to form a lower entropy molecule, okay. So at low temperature or a lower temperature favor spontaneity, okay, greater and better contact time to form the parts to assemble in the correct way, okay. So low temperature favors spontaneity, and the opposite, high temperature hinders spontaneity, okay, decreases the probability of the reaction to taking place because the contact time is too short and too much kinetic energy and so on, okay. Okay, so, well, let's try now to build a spontaneity table, okay? Given that we have all these assumptions and conclusions, okay, in terms of combinations of being exothermic or endothermic, or having more disorder or less disorder in the process. Okay, let's try to fill this table, and then we are going to propose a definition of what we are calling Gibbs free energy, a measure of the spontaneity of the process. Okay, so first one, this case here. Okay, exothermic, and the process releases energy, and the process increases disorder. So I would say this is a very spontaneous. Why? Because if you need energy, you have it, okay? And if you need to create this disorder, no problem. This is taken into account. So the process is spontaneous in this situation, okay? Let's consider this one, endothermic and less disorder. The process must absorb energy, and in addition, the final result must be or more ordered, must have a higher level of order or a lower level of disorder compared with the reagents in the beginning. So this is very unlikely to happen, okay, because it must absorb. In addition, it must reduce disorder. So I would say this process is non-spontaneous in the indicated sense, of course, okay. This one, the process is endothermic, it absorbs energy, and you have more disorder. So in this case, we have already seen it's spontaneous at high temperature, Okay, it's well, we're going to make the calculation, but it's like nitrogen reacting with oxygen, giving NO or NO2. Okay, so it's spontaneous at high temperature. And this other one here, okay, exothermic, it releases energy. So releasing energy favors spontaneity, but reducing entropy unfavors spontaneity. So in this case, it's also spontaneous or conditionally spontaneous, and we already know that it is spontaneous at low temperature. Okay, like assembling parts of a car to bring about a car. Okay. Well, a very common example is of temperature dependence is water being frozen to ice and ice melting to water. Okay, you know, in the sense, water melting, water solidifying to become ice. This is a spontaneous process at low temperature. Okay, so the sense indicated here by 1. Let me write it here for you. So 1. It's spontaneous at low temperature because water becomes ice at low temperature. Spontaneous. You don't have to do nothing. Okay. In the opposite sense, ice becomes water spontaneously at high temperature. You have a block of ice at high temperature, let's say 30 degrees, and you turn your back. When you look at it again, it's everything transformed to water. Okay, so it's spontaneous at high temperatures. That's the meaning of this dependence. Okay, so this spontaneity table is very important because we're going to propose right now how this measure of spontaneity can be calculated, assessed in terms of these variables. Okay, we already know it has to do with enthalpy and entropy, but also with temperature. So we must propose a variable to measure spontaneity that takes into account delta H, enthalpy, also entropy, and also temperature. So we have to mix these variables somehow, okay, to, let's say, give birth to this measure of spontaneity. Okay, so who did that was Gibbs, again. So he proposed that this thermodynamic potential is a function of delta H and another function of entropy and temperature. Okay, so these functions, generic functions, are A and B. Okay, so A is a function. We're going to see what it can be. Okay, and B, it's another function. Okay, of two variables, like here. Okay, so let's try to figure this out. Okay, well, he also wanted that this potential vanishes when the system is in equilibrium. If I have in this case here, okay, so if I have a small sphere, for instance, in this situation here, okay, in this situation, so it's indifferent, it's in equilibrium, okay, if it can continue moving, it can stay in a fixed position. So in this case, delta G is 0, okay, because it's in equilibrium. Okay, in this situation, delta G, in this situation, the ball going downwards, okay, that's the sense, the indicated sense of a process. In this situation, okay, delta G must be negative because in this case the process is spontaneous. Okay, in this other situation here, the ball moving upwards, okay, in this situation the process is non-spontaneous. I have to force it somehow. Some external force must be acting on the ball in order for this ball to move up. Okay, so in this case delta G must be positive. Okay, so this variable that we're going to build, delta G, or G actually, for G for Gibbs free energy, it has to behave like this. In equilibrium, delta G is 0. And for a spontaneous process, it's positive, and for a non-spontaneous process, it's positive, and for a spontaneous process, it's negative. Okay, so we're going to take these into account, the definition of this variable as proposed by Gibbs here. Okay, and also we're going to try to harmonize this with our spontaneity table, okay, that we have already elaborated. Okay, so a proposition, now we're trying to combine these variables, entropy and enthalpy. Okay, a proposition is this one. Okay, so function A of delta H is simply 1, okay, and we're proposing that delta G is proportional to delta H, okay, and proportional to something times delta S. Okay, so this is a proposition. Delta G, or spontaneity variable, okay, is proportional to delta H, okay, and proportional to plus delta H, and also proportional to minus delta S. Only that delta S must be multiplied by something here, because I cannot add these two variables because they have different physical units. Okay, and we also have to consider temperature in the equation. Okay, so we're going to propose that multiplying delta S by T, okay, minus T. Okay, this takes the problem of proposing B, solves the problem of proposing B. Okay, and finally, we're going to define delta G as being delta H minus T times delta S. Okay, let's see if this variable, if this definition satisfy our spontaneity table. Okay, I'm trying to induce the definition for you. Okay, I could have simply announced delta G is equal to this, but no, I'm trying to induce the definition for you. Okay, so let's see if this definition satisfy our spontaneity table. Okay, if I have, I don't know if I'm doing this if I have delta H negative here, okay, let's see if we are okay in this region here. Okay, delta H negative and delta S positive. Okay, delta H is negative. Let me put some numbers here, like minus, plus, sorry, sorry. We are in this, analyzing this case, okay, delta H is negative, so minus 5, okay. Also, delta S is positive, okay, and multiply by the temperature. Let's say that I have 5 as delta S. Let's say that temperature is 1, and I have the minus sign here. So this is equal to minus 10, okay? So these numbers are okay in this situation, and we have minus 10. Minus 10, going back to, here, minus 10, it's negative, so the process is spontaneous. So, okay, we already satisfied this situation. I'm going to make only one more, okay, just to be sure everybody understands, okay. Now we're going to analyze this situation. No, not this one, a conditional one. Let's analyze, for instance, this one, spontaneous at low temperature. Okay. So in this situation, delta H is negative and delta S is positive. So let's suppose we have the same numbers, minus 5 here. Delta S is negative. Okay. But delta H is negative, but delta S is also negative. So here I have, let's say, minus 5, and suppose the temperature is 1 here. So now we have minus 5 plus 5, I have 0. Okay. Let's see at low temperature. Okay, so 0 means equilibrium. We're on the verge. But let's see, instead of 1 degree here, I can have, for instance, 0.1. Okay, minus 0. So here I have minus 5 plus 0.5. Okay, so this is minus 4.5, which is negative. So it's okay. It's negative, meaning it's spontaneous at low temperature. When the temperature decreases, the process, this variable, becomes more negative, so more spontaneous. Okay, so we can do this for all situations here, and we conclude that this is a correct definition for what we want to measure spontaneity of a process. Okay, so we can simply define now that because, well, we propose things in terms of variation of Gibbs free energy, and now we can define a state variable as being G, Gibbs free energy, equals to H minus Ts. Okay, and we know that when dG is negative, like in here, okay, the process is spontaneous. If I don't do nothing, simply let things happen, the ball will go downwards, okay, because it's a spontaneous process. Let's see a practical application of this variable. Okay, let's see again CO reacting with O2. Okay, so we have carbon monoxide reacting with oxygen at 1 atmosphere to give CO2. Everything in gaseous state. Okay, so it's like having a reactor. It may be a reactor like this. CO is the fuel, okay? O2 is the oxidant. And an important point here, we're going to calculate right now at room temperature. T5 means our environmental temperature reference, okay, that we are going to indicate by T5. Okay. Well, the energy content of the combustion products is inferior to the reagents. So this process releases energy. Okay, we're going to come to this conclusion in a few moments. Let's see if this reaction is spontaneous or not. Okay, so this is exactly one of those cases, two cars or parts of a car bumping into each other and forming a single car. So entropy decreases, okay, but we know that it is exothermic. It releases energy, okay, and this energy can be used to form these particles, okay. So this is the case where the process may be or may not be spontaneous depending on the temperature. Let's see how it works. So we have our definition. This reaction is taking place at 25 degrees, T5, okay? And we have our definition of delta G. Okay, so applying the first law of thermodynamics, okay, to this system. Here the control volume is around here. Let me, oops, sorry, get my pen. Here the control volume is here, okay? This is my control volume, okay? So delta H equals the sum of all products minus the sum of all reagents, okay? And this, remember, this is heat. Following our convention, this is heat absorbed, okay? This is heat absorbed by the system. If it's negative, this means that it is released, actually, okay? Well, we also have this equation, entropy, for entropies, okay? That's the same equation, okay? And we're going to apply this. To apply these equations, we need some charted data. They are here, okay? So formation enthalpy of CO is given here. So these are simply charted data, okay? Formation entropy of CO is given here. Then for O2 is 0. This is entropy formation. Okay, same for CO2, and we're going to need the specific heats of CO, O2, and CO2. Okay, so let's use this data and write down calculate all terms of Gibbs free energy. Okay, so when we replace our data, okay, so this number 1, let me go back to the equation. Okay, you must think in terms of this equation here. Okay, I can write it here. 1CO, okay, plus half O2 giving CO2, 1. Okay, 1 molecule of CO2. Okay, so here we have the products. We have only one product, which is carbon dioxide, sorry. Okay, so this number 1 here, okay, is correspond to this number 1 here. Okay, and 393 is where is it? Is the enthalpy associated with the formation of CO2. Okay. Again, on the other side, or from the left side of the chemical reaction, okay, this number 1 here actually is this number 1 here, and minus 110 is the enthalpy of CO, okay, carbon monoxide, and then 0.5 times 0 is the enthalpy of formation of O2. Okay, so making all the calculations, we have this result here. Delta H equals minus 282.98. So the process is exothermic. Okay. Now let's calculate entropy variation. It's the same logics. Okay. So 1 times 213. 213 is entropy variation of CO2. Okay. 1 times 197. 197 is the formation entropy of CO. Okay, and 0.5 times 205. 205 is the formation entropy of O2. Okay, so when we do all the calculations, we have this result. Okay. Okay, now we are ready to combine all variables or terms. We calculate all these terms. Okay, delta H, delta S, and T. Okay, delta H minus 282.98, delta S minus 86.5. Okay, and temperature is 25 degrees, which is 298 Kelvin. Okay, so when we add these terms, make all the calculations, we get delta G minus 257.203. And the minus sign means that the process is spontaneous in this sense, okay, in the indicated sense, at 25 degrees 1 atmosphere. Okay, so we know, and we already knew this, okay, that CO in the presence of O2 at room temperature and pressure reacts to give CO2. Okay, this is okay. But we know that this process is conditionally spontaneous, depends on the temperature. So let's try to figure out beyond which temperature the process is not spontaneous anymore. Okay, so let's try to do. And for this, we're going to apply Hess's law. Okay. Well, we already did the process in this sense here. Okay, we want to calculate at a temperature different from the ambient temperature, T5, which is 25 degrees by convention. Okay, so instead of calculating in this given sense, we're going to consider the following. Okay, instead of reacting at, I don't know, 1000 degrees here, we're going to cool all reagents down to 25 degrees. So we remove heat from CO, we remove heat from O2, okay, we remove these amounts of heat so that CO and O2 now are at 25 degrees, okay. Then we allow the reaction to take place, okay. So CO and O2 react at 25 degrees, they release heat and form CO2, okay. And then finally we're going to heat the products to the initial temperature, 1000 degrees, so we must add heat here, okay. What Hess' law says is that when you apply, you can apply the first law of thermodynamics here, okay. Let me make a drawing here. You can apply the first law of thermodynamics here, or you can apply it like this. You can make this calculation here, okay. You can do both things, okay, to calculate. So we're going to do this second démarche, okay. And so the delta H, this is the heat absorbed by this yellow control volume, okay. So it's equal to the heat that we removed from CO and O2 in order to bring them from 1000 degrees to 25 degrees, plus the heat released by the reaction, okay, plus the heat absorbed necessary to reheat CO2 from 25 to 1000 degrees, okay. So this is first law of thermodynamics, but according to this process here, okay. And what Hess' law says is that it is equal, okay. So it's simple. The two quantities related to cooling and heating we can calculate like this, since they can be modeled as perfect gases, okay. So deltas mean these deltas means a quantities of heat removed or added to the components, okay. So we can calculate this using the specific heats of each component K, okay. And since it's a perfect gas, the specific heat is constant. We can take it out of the integral. We get delta T. So this is a very known. The heat absorbed or released is equal to the number of moles, N stands for the number of moles or mass, okay, times the specific heat times delta T, okay. So this is a very well-known expression, okay. In our case, we already have these charted data. When we make all the calculations, okay, I'm going to show you only one. So specific heat of CO2 is 29.14 joules per mole, okay. So minus 29.14 times T minus 298. Minus, why the sign minus here? Okay, I want to see if you understand this. This sign minus, I'm going back one slide, it's because we are removing heat from the system. And remember, when we give heat to the system, we are considering this a positive heat, okay? When the system releases heat, the system meaning in this case CO, okay? When CO releases heat, this means negative, okay? So negative here is because heat is being removed from CO. The same thing happens to O2, okay? So when we make all the calculations, we get this number. In function of a generic temperature here, okay? So the same thing for O2 and CO2, okay? So these terms here, the amounts of heat necessary to cool down from 25 to 1000, and the amount of heat necessary to heat up from 25 to 1000 degrees, okay? Now we only have to calculate this, but This term here, the heat of reaction at the reference temperature, 25 degrees, we already know. We calculate this in our first example. Okay, so this number is minus 282.98. This, if you don't remember, I'm going to refresh your memory. We did this calculation, oxidation occurring at 25 degrees, okay, and we make all the calculations, and we got delta G, delta H minus 282.98, okay. So this number here is the heat of reaction at 25 degrees. Phi here means at reference temperature, 25 degrees, okay. So we are using this number here, okay. It comes here. So we get this expression, okay. Delta H of the chemical reaction is given by this formula, and we can calculate for different temperatures, for instance, okay. Okay, so the process for entropy, because we did this to calculate enthalpies. Now we need to calculate entropies. So the process is exactly the same. I'm not going to spend too much time here. So, okay, we are still applying Hess law. Instead of applying first law of thermodynamics in the direct sense, we're going to take a detour, okay, and we're going to apply the first law here. Okay, so it is exactly the same. Only that now the variations of entropy associated with cooling and heating, okay, I can still calculate in terms of the definition. Remember the definition of entropy, okay, entropy, or ds, equals to dq over t, okay, and dq I can calculate as Cp dt, okay. So that's what we are using here, okay, in this place here. Okay, so we're making all the calculations in a very analogous way, and we get these formulas here. The entropy variations associated with cooling and heating, okay, we get this formula here. Ln of T over T phi is the integral, is when I perform this integral. Cp is constant, and I get integral of dt over T, which is Ln of T minus Ln of T phi, okay. Okay, let's move on, and now we only need to do the calculations. We have this formula. I replace all data that I have for CO, for O2, and for CO2, okay, and I get these functions of T. So the entropies, in terms of variations of entropies in terms of the temperature, okay, and when I apply Hess law, I get here, okay, and replacing all that we have, we get this final result here, which is the reaction entropy variation in terms of the temperature at which the reaction is occurring, okay. Okay, now let's put everything together and calculate delta G, because we want to know what is the temperature beyond which the reaction is no longer spontaneous, okay. So replacing delta H, okay, here, that's our delta H, and now replacing delta S here, okay, and T here, okay, we get this final result here, okay, a function of T multiplying by Ln of T inside here, okay. Now we can make a graph like this. We have delta G in function of temperature, and in fact in Kelvin, okay, absolute temperature. Okay, so at low temperatures, well, this is too low, excessively low temperatures, but anyway, starting from 0, which is, well, unrealistic, but you know that around 2,600, oh, I have the number here, 2,679 degrees, delta G becomes 0, so the process is neutral. And below this temperature, 2,679, the process is spontaneous. So in this region here, the process is spontaneous, okay? Process is spontaneous. In all this region here, the process is spontaneous. And of course, beyond this, above this temperature, the process is non-spontaneous, okay? So we know that at this very high temperature, CO bumps, shocks with O2 at so high speed that they don't have time to form CO2. They have too much energy, so they bump and bounce back, okay? So that's the reason why this reaction is non-spontaneous in this indicated sense here, okay? It's obvious that if it's non-spontaneous in one sense, it is spontaneous in the opposite sense, okay? So at very high temperatures, such as 2,600, CO2 molecules, let me draw here, CO2 molecules, CO2 molecules, when they bump, they have so much speed that, well, this is going to be a very nasty crash, okay? So in this situation, you may have COO, let's say COO, and, well, they can mix. This C may join this O, this C, this O, and so on, O2 and CO, okay? So this can happen at very high temperatures, and the reason is you have to have enough kinetic energy in order to disassemble the molecule in its constituents, okay? So this is why the process is spontaneous in the other sense, in the opposite sense, okay? Okay, so we have our variable which is capable of assessing how spontaneous a process is. Remember, we started talking about exergy, and we want to calculate, to define a way of calculating the amount of exergy, the exergy content of a substance when chemical aspects are considered, okay? So let's move in this path. Let's remind our definition, okay, of exergy. We have these components. We have the term associated with thermodynamic exergy, okay, potential, kinetic, and chemical energy. And the fundamental idea of defining exergy is that the capacity of generating useful work, mechanical work, or exergy, or organized energy, is a combined environmental system property. So I must take this, the key word here is combined, okay? I must define what is the environment when I'm talking about chemical aspects, okay? Let's see this. If our reactions are taking place in the atmosphere, okay, so the environment may be considered to be the atmosphere. And this is its chemical composition at low altitudes. I'm stressing this because the atmosphere varies a lot along the altitude here, okay? So this composition, traditional composition, 78, 21, 1%, if you want to consider 3 components, nitrogen, oxygen, and argon, okay? This refers to the troposphere, okay, which contains 80% of Earth's atmosphere. We're going to use this number at the end of our class. Oh, no, not at the end of our class. I have so much to say, I must speed up today at 70% of our class, okay? So, for us, the environment is the atmosphere. Let's define this. It can be different, okay, but let's assume it's like this. Just to give you the definitions, because the definition of a chemical exergy of a component, of course, depends on the environment, okay? So if your chemical reactions are taking place in Mars, for instance, on Mars, so you must use Mars's atmosphere as your reference environment, okay? Okay, and well, there are two aspects here. You may have chemical reactions or not, and you may have different compositions compared with your reference environment. Okay, so let's analyze these two aspects separately. Okay, so first I'm going to deal with species that are present in our atmosphere. Okay, so nitrogen, oxygen, argon, and so on, carbon dioxide, and so on. Okay, and then we're going to consider chemical reactions. Okay, okay. So for the moment, we're not going to analyze chemical reactions. So what is our problem right now? Our problem is to assess the chemical exergy of gases, okay, of atmospheric gases. So let's consider nitrogen. Suppose I have 1 cubic meter, or a certain amount of nitrogen, at 1 bar, 25 degrees, which is our reference temperature and pressure. Okay, so let's say I have a certain volume here, 100% nitrogen. This is the concentration of nitrogen in this control volume here. Okay, and we want to calculate its Exergy content. Just an observation here. I'm going back two slides. I'm using the letter X to refer to Exergy, okay? And now I'm going to need the letter X for other definitions. So I'm going to switch to E, okay? So E now, from now on, is going to stand for Exergy, okay? CH stands for chemical, okay? So the index CH stands for chemical, and N2, of course, stands for nitrogen, okay? So, by definition, Exergy is the maximum amount of work, so reversible work, that I can obtain from the substance. Okay. So, what can I do? I know that if I have N2 at 1 bar, and if I release it to the environment, the concentration of N2 in the atmosphere is 78%. This means that its partial pressure is 78% of 1 bar, which is the environmental pressure. Okay, so I have a lower nitrogen pressure here, and this means that I can expand this nitrogen to the atmosphere and obtain work here. Okay, so the maximum amount of work that I could obtain in this process is going to be our chemical exergy. Okay, so that's what I'm going to do. I'm going to allow this expansion to occur because here I have nitrogen at 1 bar, and in the atmosphere the partial pressure of nitrogen is only 0.78 bar. Okay, so I have a lower pressure. So the pressure is going to, the total pressure is the same, 1 bar, okay? And the, let's say, total temperature is also the same, 25 degrees and 25 degrees, okay? So the process, this expansion is isothermal, okay? So the process here is going to be isothermal, and this means it's going to absorb heat, no problem. Okay. And another important formula here is that the partial pressure of N2 in the atmosphere is its molar concentration times the total pressure. And this is why I switched from X referring to exergy to X referring to molar concentrations, because that's traditionally used here for molar concentration. And now we are using E for exergy. Okay? So we know how to calculate this. Isothermal expansion, when we apply the first law of thermodynamics here, I obtain this equation here. Okay? And I'm also using the fact that N2 in this situation may be considered a perfect gas. Okay, so this work I know how to calculate. It's very simple. Okay, it's RT0 times Ln of the partial pressure or the partial pressure of N2 in the environment divided by the total pressure. Okay, so it's easy to calculate. But let's calculate chemical exergies of some atmospheric gases, just to show you the results and how can we use these results. Okay, first, chemical exergy of nitrogen. So minus RT0. I'm going back one slide just to, and I'm going to write this down. In this expression here, okay, in this expression here, this term P, the partial pressure of N2, okay, divided by total pressure, I can write in terms of this equation here. Okay, so this work may be minus RT divided by Ln of its molar concentration. Okay, because of this relation here. So that's what I'm using here. Okay, I'm using this fact here. And when we replace the proper numbers, minus 8.314 is the gas constant. Okay, T0 is 25 plus 273.15 to switch to Kelvin. Okay, and Ln of 0.781, its molar concentration. Okay, here. When we do the calculations, we get this final result. So 613.2 joules per mole. The same thing for O2. Okay, here. So when we do the calculations, everything is the same. The gas constant is the same, temperature is the same, only the concentration is different. So we get a bigger number now. Okay, and the fact that the exergy content is higher means or implies that extracting O2 from the atmosphere requires more exergy than extracting when compared with extracting N2, because its molar concentration is smaller. Okay, I can figure this out from here because I'm considering the process in one sense, but I can also consider in the opposite sense. For instance, here I have oxygen, or let's take O2. CO2, sorry, CO2, where is it? Here. I have CO2 at very low concentrations in the atmosphere, and I want to remove CO2 from the atmosphere. Okay, why is that? Because, well, I want to avoid greenhouse effect. Okay, so to remove CO2 from the atmosphere means to compress it from 0.04% of a bar times 1 bar. Okay, so I'm going to compress from this very low pressure to 1 bar. So I'm going this sense. So I have, in this situation, I have to add work to this. So I have to have a compressor. Okay, and since when the concentration is very low, this initial pressure is very low. The final pressure is the same, 1 bar. Okay, initial pressure is very low, so I have to add more work here. I have to compress even more. Okay. So chemical exergy, you may consider it from the state of the substance to the environment, or the work the work obtained from this process in this sense, okay, or the work supplied on the other sense, okay. Hope I made myself clear. Other two calculations, okay, for argon here and for CO2, okay, CO2. You see, since the concentration is very low, the exergy content of CO2 is very high. We're going to use this number in a moment because I want to assess the amount of energy necessary to remove CO2 from the atmosphere in order to avoid greenhouse effect. So we're going to use this number. Okay, and as I said, depending on your reference environment, you can have different expressions. Okay, so let's try to generalize these expressions, because all these calculations I did considering our own atmosphere as the reference environment. Okay, so if I have a generic environment, of course at the same pressure and temperature, P0, T0, and the components of this environment are listed here, okay, and the corresponding molar concentrations are here. So when we do the calculations in this case, in order and also if I have a mixture of gases here, of the same gases, okay, so these components are the same ones here, only pressures, only the molar concentrations are different, because total pressure and total temperature is also the same. Okay, so when we do the calculations, we get this formula for the chemical exergy. The interesting thing is that you have this term here. Okay, this is very interesting. Okay, because you see that the only thing that enables production of work or forces work to be supplied to the process is the existence of differences in composition. Okay, so it's the compositional differences that enable the production of work. Okay, this is exactly, or remember the first slide was the osmotic power plant. That's exactly how it works. We can assess, we can calculate the amount of power that you can generate from if you have salt water and sweet water, and somehow you can put this into contact, and you want to assess the amount of work that you can generate, you can use these expressions or similar expressions. Okay. Okay, so yeah, just elaborating a little bit more. Okay, our chemical exergy is given here. This is the same expression here. I just transfer to the other slide. Okay, and when we replace what we already know, okay, we get this number here. Okay? We get this formula here. Okay, so the first sum is the chemical exergy, based on a model environment. Okay, and these molar concentrations here define what we could call as a chemical distance to the environment. As I'm saying, what enables production of work is difference, or we can consider a distance. So the more distant or the more different a system is from its reference environment, the more we can produce work from this substance. Okay, and if we have no distance or no difference, meaning that all concentrations are the same, okay, then its Exergy content is 0. We cannot obtain work from this situation. The only possibility is having different pressures and temperatures. Okay. And as I'm saying, as I already said, chemical exergy can also be defined as the minimal amount of mechanical work necessary to reconstitute the state and composition of a system from the environment through compression chemical reaction. We did not analyze chemical reaction, okay, but we can do it. We're going to do it in a few moments. I just want to elaborate an example with you before going to chemical reactions. I'm controlling my time because, well, I don't know if I'm going to be able to cover all the subject today. Okay, so the example now is the following. I want to recover the pre-industrial revolution atmosphere. Okay, we know today we have almost 400 ppm CO2. Okay, and roughly, and before 1800s, we had 300 ppm, roughly speaking, CO2. Okay, I want to go back from 400 to 300, and we know this increase from 300 to 400 was due to industrial revolution. Okay, so in order to do this, what I needed was to devise a machine that removes CO2 from the atmosphere somehow and store this mass of CO2 somewhere other than the atmosphere. Okay, so we want to remove the carbon dioxide that we emitted during all this period, from the 1800s to today. So if I manage to build this machine, it can be by liquefaction, for instance. I can construct a kind of a liquefier, okay? And I can liquefy CO2 from the atmosphere and store CO2 somewhere. And it's obvious that this machine is going to need work because actually we're separating CO2 from the atmosphere. So this machine actually takes air, let's say air plus CO2 mixed. When I say plus, I mean mixed. Okay. Then I have CO2 here, CO2, and I have air. Okay. So this is separation machine. We already analyzed this. We know that I'm going to need work for this operation, okay? Because this is our separator. I need work. I need to invest work. The question is this feasible? Because this amount of energy, this amount of work may be impossible, okay? Maybe, I don't know, 2 or 3 times the total energy of the sun, okay? But let's suppose it's feasible. If it's feasible, what is the minimum amount of exergy necessary, okay, to remove CO2 from the atmosphere so that its concentration, that's the initial problem proposition, okay? So we want to know if the process is feasible, if this amount of work here is tractable, okay, and if it is, what's the minimum amount? Okay, the minimum amount necessary for this. Let's do this calculation because we have everything that is needed for. In terms of distances, remember the concept. I said that these concentrations defines a kind of a distance from our reference atmosphere. Okay, so our reference atmosphere is the environment, and we want to bring the environment or from its initial situation to the composition associated with the pre-industrial era. The difference here is very, very slim, actually. You see, those are exact numbers or correct numbers. The concentration today, CO2 concentration today is 0.036%, okay, and before the Industrial Revolution, 0.0300%, okay. So if we remove CO2 from the atmosphere, so that this 0.036 drops to 0.0300, okay, and the other concentrations will change according to this equation here, okay. So the changes are actually very small, significant for CO2 because it's already very small, but for nitrogen and oxygen, the concentrations, the molar concentrations, drops on the third case, okay. So nitrogen, for instance, drops from, increases actually 78.08, 084 to 78.088 or 889, okay. So if you remove CO2, its concentration drops and the other components' concentrations rise, okay. We know how to calculate this, okay. The minimum amount of work is here. It may be positive or negative, depending on the sense of the process or who you're calling, or who you're defining to be the environment, okay. So we're going to use this expression. I transfer this expression here just for reference. So let's apply it. Minus R, this is the gas constant, okay, times temperature. We're doing everything at room temperature, 25 degrees, times the concentrations, plural, okay, 0.78088, okay. The formula goes on, it's very long, so I didn't bother to write it down. We get this number. Okay, so the minimum amount of work for this process is minus 0.01315 joules per mole. Okay, joules per mole, if I want to, and this is per mole of atmosphere, okay. I want to calculate this for the whole Earth. So I don't know how many moles of air I have, but I know the mass of air in our planet. It's given here, 5 exakilograms. Exa is 10 to 18, okay. So our mass is, our atmosphere mass is roughly 5 exakilograms times my specific work times molar mass of air, okay, 28.97 grams per mole, okay, if I'm not mistaken. Right, if all the calculations are correct, yeah, I see a kilogram here. I'm not sure if I made all the calculations correct. Yeah, sometimes I do this. I hope I did all the calculations correctly, but this means that this amount of energy is 2.2 exajoules. You know, this is exa seems a very big number. It is actually, but the world energy consumption, annual energy consumption, is around 550 exajoules. So it's not very much actually. If you calculate in terms of power consumption, it's equivalent to 4 days of power consumption. Okay, so yeah, I have a doubt now. I'm looking for grams here. This means that well, if I made a mistake here, this must be multiplied by 10 to the third power. Okay. Well, anyway, it's not 1 billion years. Okay, it's 1,000 days or 4 days. It's a huge difference, but at least this first question here, I think it's okay. It is feasible. It is really feasible. Okay, you don't have to wait 1 billion years for this. Okay, when you compare our annual energy consumption. Okay, Please, if you have the time, verify this number. I'm going to do it myself, but next class we can verify this. Okay, sorry for this. Well, anyway, let's stick to this result here for the moment. 4 days. 4 days seems to be a very low price to pay to recover our atmosphere. Okay, but remember, this is the minimum theoretical work. Okay, and theoretical. Remember, this came from canceling all exergy destruction terms, or said differently, or entropy generation processes. That means all processes in our CO2 machine are reversible. All processes have the maximum possible efficiency. Okay, so this is the minimum work. You know, the actual work that you're going to need is greater than this minimum number. Okay, and what happens in practice is that, as I'm highlighting here, the efficiency of the process tends to decrease. Okay, let's say mechanical efficiency of the process or exergetic efficiency of the process tends to decrease as the molar fraction of the element that you're removing decreases. Okay, so and it can be very small. So if we have to wait to spend 1,000 days to remove CO2 from the atmosphere times 100, okay, so this is 100,000 days, okay, of our energy consumption, daily energy consumption. Okay, so this may become very significant. Okay, just a pointer here. All these calculations, and a very interesting book on this subject is this one. Okay, if you're particularly interested in this book, in this subject, I really recommend this book. Okay, it's very interesting. Okay, so now remember, I'm dealing with a chemical exergy, and we had two possibilities: with or without chemical reactions. Okay, now we did all analysis without chemical reactions. Now let's try to assess the chemical exergy of a generic substance that is not present in the environment. Okay. Okay. So well, this subject is very vast. Okay, and for practical reasons, I'm going to model my substance like this. Okay, why? Because this represents almost any type of fuel that you use to generate energy for practical purposes. Okay, so gasoline, kerosene can be modeled like this: a generic molecule. So I have small a atoms of carbon, small b atoms of hydrogen, okay, here, and small c atoms of oxygen. This is my generic substance. Okay. Another variable here to be highlighted is it is at a pressure P0, and its molar flow rate is in F. The letter F stands for fuel. Okay. So I'm injecting this fuel in a reaction chamber, okay, a burner. I can generate work from this process. I know already that the maximum amount of work is going to be its chemical exergy, okay. But I also have to consider that the environment, because the process is taking the differences, all kinds of differences, okay, from the original state to the environment, both in terms of pressure and chemical composition. Okay, Okay, so what I'm going to, because the components are different, this fuel is not present in the atmosphere, okay, but the atoms are, okay, so I have carbon atoms in the atmosphere, I have hydrogen atoms, the other ones here, I have oxygen atoms, okay. So the idea is that I'm going to use some of those components, oxygen for instance, since the environment has an infinite supply of oxygen, I'm going to allow this oxygen to react with fuel in order to generate components that are present in the atmosphere. Okay, so that's what's going to happen. Okay, I'm going to get some amount of oxygen from the atmosphere, and by some I mean exactly this amount, A plus B divided by 4 minus C divided by 2. A, B, C are the number of molecules here, okay? And this is done in order to balance the equation. So this is stoichiometric quantities, okay? So when I combine this amount of oxygen with 1 mole of this molecule, I have A moles of CO2 plus B divided by 2 moles of H2O. Okay, and CO2 and H2O are present, are components of our atmosphere. Okay, so I'm going back one slide. If the chemical substance is not present in the atmosphere, in the reference environment, I'm going to use one or more components here to react in order to form the same components here, okay? It doesn't have to be all, but as in here, I'm only forming CO2 and H2O. I'm not forming O2, for instance. Okay, so okay, when we apply the first law of thermodynamics, we have this. Okay, so work, and those are specific quantities. Okay, I'm dividing everything by the molar flow rate of fuel. Okay, so the amount of heat given to, supplied to the control volume, okay, and this is to respect our convention, divided by the molar flow rate of fuel, in order to have a specific quantity here, okay, minus a positive amount of work, which means it's coming out of the control volume, okay, here. So this is equal, according to the first law, to enthalpy variation, okay? Products minus reagents. So I have A times CO2 enthalpy here, plus B divided by 2 enthalpy of H2O, okay? Minus fuel's enthalpy here, plus oxygen's enthalpy, okay? HO2 times the amount of oxygen entering the control volume, okay? And the same can be done. This is the first law, and this is an entropy inventory, or the same Exergy inventory, okay? So I get this expression here. It's exactly the same, okay? Entropy generated entropy associated with this heat flow here, okay? Fuel's entropy, SO2 entropy, and so on. And I have also entropy generation term here, okay, as I mentioned before. So I have these two expressions here, okay. Well, I just transferred the expression here. So this is entropy inventory, okay, and if I rearrange the terms here, okay, T0, well, I'm just multiplying everything by T0, okay, and if I replace this heat from the entropy balance into the first law's expression, Okay, so I'm replacing this expression here. I get this result. Sorry. I get this result. Okay. So this is still the first law, but the heat associated I'm calculating from the entropy inventory. Okay. Well, now what I'm going to do, I'm going to rearrange some terms, and also I'm going to cancel the entropy generation term. Why is this? Because I want to calculate the maximum amount of work. So the maximum amount of work happens when all processes are reversible, and this means that there is no entropy generation. So this term goes to zero, and this term becomes the specific fuel's chemical exergy. Okay, so specific fuel's exergy is this term here. Okay, we're going to simplify it a little bit further. Okay, but an important observation right now: enthalpies and entropies are calculated at T0 and at the corresponding partial pressure of the environmental component. Okay, because I'm going back a few slides just to show you the chemical reaction. Because you have T0 1 bar, T0 1 bar. The pressure and temperature is not varying. Okay, but since molar components are varying, okay, it's the corresponding partial pressure will vary. Okay. So, for instance, here, this enthalpy of CO2 must be calculated at T0 and at its partial pressure. Okay. It is true that the pressure influences on enthalpy is small, but you can be precise. If you want to be very precise, you're going to consider the pressure. Okay. So, doing all the calculations. Okay, this is we're going to do these calculations. So this is the chemical reaction. Okay, 1 mole of fuel plus this amount of moles of O2, giving A moles of CO2 plus B divided by 2 moles of H2O. In this case, the phase matters. Okay, so H2 is it's a gas. Okay, also CO2. Also O2, but our fuel, I don't know, it may be paraffin, for instance, it may be solid, liquid, or gas. Okay, let's make our calculations considering everything ideal gases. If it's an ideal gas, this means that the enthalpy depends only on temperature. Okay, so in where I see an enthalpy, I can write it in terms of the corresponding temperature. Okay. So this is the expression we obtained in the last slide. The difference is that where I can consider an ideal gas, I'm making explicit that the enthalpy depends only on temperature. Okay, and this is the case here. Okay, so moving further, yeah, and also when I have mixtures, for instance. Here, entropy depends on pressure, so I'm explicitly calculating in terms of its corresponding partial pressure. Okay. Okay. Is there some doubt here? Because I'm trying to elaborate all the definitions and mathematical manipulations. If you have doubt, you please interrupt me. But I really recommend you to do these calculations by yourself, okay? Because it's very hard to grasp the concepts, not the concepts, but the mechanics in slides like this, okay? So I really recommend that you do these calculations by yourselves, okay? Okay, so continuing, okay, for an ideal gas, I also can neglect the influence of pressure. Okay, this is for an ideal gas. This is a known expression. And replacing everything I have. So enthalpies here, okay, and entropies here. And I have this interesting term here, okay. Okay, so you see I don't know if you remember the definition of we just obtained it, I don't know, half an hour ago. Enthalpies, or enthalpy, this is enthalpy, these are enthalpies, okay, minus temperature times entropy. Okay, so this term here, okay, let me write it down, try to induce this. Okay, enthalpies minus temperature times entropy. What was this definition? This was Gibbs. We just obtained this. Okay, so we can use the definition we have from Gibbs and write the chemical exergy in terms of Gibbs free energy. So when we do this, we get this, we get this less complicated formula, okay, in terms of Gibbs free energy of the fuel, of oxygen, of CO2 and H2O, plus the interesting term that I'm going to explain in a while, okay, in a moment. Okay, so this is the formula that we have to calculate the chemical exergy of any fuel that can be modeled as something like C small a, H small b, O small c. Okay? No, sorry, yeah. Okay. Two important observations. Okay, let me get my pointer. First, the first term in the right side corresponds to the reaction's total Gibbs free energy variation. Okay, that we have already realized. Okay, therefore, the more spontaneous, the greater the chemical exergy. Okay, because we already knew that if delta G is negative, the reaction is spontaneous, and the more negative, the more spontaneous is the reaction. Now, we can infer this, that if the reaction is very, very, very spontaneous, its chemical, its exergy content is going to be very high. Okay, so spontaneity is related to exergy content. Okay, another important observation is that it's a practical observation. Okay, because since you're calculating Gibbs and enthalpies and entropies of different substances, okay, and they may have different reference states, you must bring all these references to a common reference. So it's a practical advice, actually, that to bring all calculations to a common energy reference, the Gibbs free energy and also enthalpies and entropies can be calculated according to the following formula. Okay, so I'm giving here. And well, when we consider all this, we have this final formula for Gibbs free energy. Okay, so you see that the component, the exergy content, is proportional to Gibbs free energy. Okay, plus this term here that actually considers the environment, the molar composition of the formed species in the environment, okay, and the molar concentration of the species that you need from the environment in order to react with the molecule, or the fused molecule, in order to form those components, in this case CO2 and H2O. Okay, so this plays a role of a matrix. Okay, this is also proportional to the distance, what we are calling distance from the environment, or to the environment, from the substance to the environment. Okay, and this this term here accounts for this virtual distance. Okay, so let's apply this to an actual case here. Okay, so we're going to to apply this to an internal combustion engine. And just to give you a hint of where I'm going to end comparing internal combustion engines to electric motors, okay, for electric cars, for instance. Okay, so let's do it. So I have an engine, an internal combustion engine. For simplicity, let's assume that our engine burns octane. Okay, so we have, this is our fuel, CHH18 in liquid form. Okay, it reacts with air, so it reacts with oxygen and nitrogen, and the quantities here are already balanced. Okay, and to form 8 moles of CO2, 1 mole of fuel is going to form 8 moles of CO2, 9 moles of H2O, and 47 moles of, well, N2. N2 is not being formed because it's not reacting. The temperature here is not high enough for N2 to react with O2. Okay, so N2 enters, all reagents enters at 25 degrees 1 bar, and at the exit we have 1 bar 890 degrees Kelvin. Okay, so the temperature increases, and well, the pressure is the same. Okay, so this is given. A combustion gas is 890 Kelvin, 1 bar. Atmospheric air, 1 bar 25 degrees. This is the mass flow rate of octane, 1.25 kilograms per minute at 25 1 bar, okay, in liquid form here, okay. And another given data is the power that you get, mechanical power, 370 kilowatts. Okay, so this is the mechanical power, the shaft power, as we say. Our model environment is here. Those are the compositions. And, well, there's some observations here, but what I wanted to say is that, yeah, concentration of H2O may vary a lot from place to place, okay? Since it's very low, it's not going to affect significantly our analysis or the actual behavior, the actual performance of this engine. Okay, so let's apply first law of thermodynamics. It's here. The heat supplied or injected into the control volume, okay, if it's negative, it's being released, minus work coming out of the control volume, okay, equals to entropy variation. Okay, so here, that's the first law of thermodynamics. Replacing all the components. Okay, here 8 moles. This is entropy of CO2. Okay, CO2. So this number 8 refers to this number 8 here. 9. This is entropy of H2O. So 9 refers to this number here, and 47. Okay, of N2 here. Okay, minus the other side, the reagents side. This is fuel's enthalpy. Okay, 1 refers to this number 1 here. Okay, 12.5, this is O2's enthalpy. So 12.5 refers to this number, and 47. Okay, so when we cancel out all terms that are 0, and we replace this charted data here. So this is fuel's enthalpy, CO2 and H2O. Those are charted data. And here I'm calculating each component's partial pressure. Okay, so I'm going to explain this one. So the partial pressure of CO2 is the number of moles. It's molar concentration times the total pressure. its molar concentration is, well, I'm going to, yeah, here. The number of moles of CO2 is 8, and the total number of moles is 8 plus 9 plus 47. Okay, so here 8 divided by 8 by 9 plus 47 is the molar concentration of CO2, times 1 gives 0.125 bar, which is the partial pressure of CO2. Okay, and we calculate its corresponding partial pressures at these two temperatures, 25 degrees and 890 degrees. And this is the corresponding results. Okay, so the same applies to N2 and to H2O. We get these results here. And moving on, and when we replace our results, we get this result here. So the heat injected into the control volume is minus 329.73 kilowatts. Minus means that it's a negative injection. So actually it is a heat removal. So okay, so heat is being removed from the control volume. Okay, this is what this sign minus means. Okay, so let's try to summarize these results, the results that we have so far. This is our engine. It's producing 370 kilowatts. We are injecting 1.25 kilograms per minute, and it's using atmospheric air to produce combustion gases at 890 degrees. Okay, we already calculated that the amount of heat removed, let's say artificially removed, is 329 kilowatts. Okay, but we also have some heat associated with the combustion gases because they are at a higher temperature than the entrance temperature, 25 degrees. Okay, we're going to assess this in a moment. Okay, well, two working definitions, or well, actually one. I'm giving two different efficiencies. First law efficiency is defined as the liquid power, mechanical power, or shaft mechanical power, okay, divided by supplied heat, the amount of heat that I'm supplying to this thermal cycle. Okay, and this we know due to the second law of thermodynamics that it's less or equal to the maximum efficiency, which is the efficiency of a reversible cycle here. Okay, so if we had a Stirling cycle, this efficiency is the maximum efficiency. Okay. Well, mechanical shaft power is actually this number here. Okay, and well, sorry, I forgot to translate everything that was in Portuguese. So sorry for half Portuguese, half English in this slide. Okay, so the amount of supplied heat actually is I can calculate from two different paths. I can calculate from the heat content of the fuel, okay, but I also can make this energy balance here, okay, because the total supplied heat is equal to what I have here as shaft power, okay, plus what's being removed here, plus what's associated with these combustion gases here. Okay, so let's try to assess. We know this. We already calculated this. Now let's try to assess this one. Okay, so to assess it, I only have to calculate the amount of heat that I have to remove from these combustion gases in order to bring them from 890 Kelvin to 298 Kelvin. Okay, so we already did this in some slides ago. Okay, so it's the same first law of thermodynamics. It's the heat removed is equal to delta H. Okay, so delta H is here. When I replace all data that I have, I get this result. So heat is being removed at this rate, 298 kilowatts. Okay, or I could have said that heat is being supplied to the combustion gases at this rate, minus 298. Okay, so it's a negative injection of heat. Okay, so when I do the calculations, I get this number. Okay, the supplied heat, the heat associated with fuel, okay, fuel injection, is this number here, 997 kilowatts. If we assess this through its heating value, okay, higher heating value, I have this charted data, I get a slightly different number, but this is okay because there are different ways of assessing this this number here. Okay, so this is not a problem actually. Well, let's calculate now the first law efficiency of this process. So shaft power divided by supplied heat. We have this number and we get 37.1%. The problem is, I don't know how much this number is. So I don't know if this is a very good efficiency or a very bad efficiency because I don't know the maximum. Okay, so the problem is solved by this other definition here, what we call second law efficiency. Okay, which is the available exergy, available meaning useful, so it's what we're calling here shaft power. Okay, so available exergy is this number here, divided by supplied exergy. Supplied exergy is the exergy content of the injected fuel. Okay, so let's calculate its exergy content. Okay, yeah, I already said that supplied exergy corresponds to the maximum mechanical power that can be obtained when fuel is being chemically transformed to the environment components. We already saw that, and yeah, we are using compounds present in the environment. Okay, so let's do this calculation. We obtained this formula here for the chemical exergy of a generic fuel. Okay, so for octane, small a is equal to 8, small b is equal to 18, and c is equal to 0. When we replace these numbers here, and also charted data, okay, we get this formula here. Okay, so this is charted data, and this is an important observation that the concentration of H2O may vary a lot in a humid day or a very dry day. Okay, it may vary a lot. So replacing all numbers, okay, here, I hope you're going to do these calculations by yourselves. Okay, we get this amount of, this is the exergy content of the fuel. Okay, well, this is exergy content. And I'm just going to multiply by the flow rate because I don't want to work with specific quantities. So that's the exergy content times mass flow rate in kilograms per second. It was given in kilograms per minute. Okay, so 1 minute is equal to 60 seconds. And well, I have moles, I have kilograms, so I'm going to divide by the molar mass of fuel, which is here, the molar mass of octane. Okay, so here in this expression, let's see, mole cancels out with this mole here. Kilograms cancels with these numbers, and I get kilojoules per second, which is watt or kilowatts. Okay, so just to show you how we deal with these units. And when we do all the calculations, we get this number. Okay, so 986.3 372 kilowatts, and this is the supplied exergy carried by the fuel. Okay. Remember, this is very important. The fuel has a certain heat content. Okay. But when I want to transform this heat content to an organized form of energy, to electricity, for instance, I'm bound to Carnot's efficiency, okay, due to the Carnot, due to the second law of thermodynamics. Okay, so that's an important way of a possible way of comparing currently. Okay, so when I replace all the numbers I have, okay, I get this efficiency here. Okay, so I know that, well, let's summarize our results. I'm supplying octane, okay, and at a certain heat content. Okay, if I burn this C8H18, I can produce this amount of heat. Okay, and if I pass this to a Carnot machine, I get this work. Okay, so this is the supplied exergy to the system, and this is the supplied heat to the system. Okay, I get 370 kilowatts at the shaft. Okay, I have this being released, being removed by cooling systems, and I have this amount of heat being removed associated with combustion gases. Okay, yeah, and well, this summarizes the example. But to conclude, yeah, I have some time. To conclude, because, well, I'm comparing an internal combustion engine which uses fuel, and actually liquid fuel. Okay, and well, you know, there's a lot of speculation in terms of electric cars replacing internal combustion engines, or electric motors replacing internal combustion engines. Okay, so let's see if this is feasible. Let's use this word. So what I'm trying to propose to you is, how do you think that batteries, in terms of a form of storing energy, okay, compares to liquid fuels, or how do they behave in terms of energy storage systems? Well, this graph here, okay, shows, it's like what I used to call operation envelope. So these are two performance indicators, okay, of these batteries, and well, you have energy density here, okay, energy density. The denser the battery is in terms of energy, the lighter it can be built, okay, because you have a huge amount of energy squeezed in a very light weight. Okay, and this second parameter here is like a volumetric efficiency. So it's the unit here. I don't know if you can. I think I can zoom. Yeah, I think I can zoom this. Oh, sorry. Sorry. Let me zoom the graph here for you. Okay. So the units here is watt-hour divided by kilograms. Okay. Watt-hour divided by kilograms. And let's say the volumetric efficiency of the battery is in this axis here. Okay. The unit is watt-hour divided by liters. Okay. So you see that different technologies, different batteries have different behavior in this envelope. Okay. The most common ones are lithium ions. I cannot see, yeah, here, okay, lithium ions. And you see, well, the better in this case, it's better to be smaller and lighter, okay? Smaller and lighter. Lighter means that you're going to, because in your vehicular application, you have to carry this battery with you, okay? So it's good to be light and also small, because it's not going to take a huge amount of space in your car. So this is batteries. But this is the important observation I had to make. These units, when I say watt hour and watt hour, this is what? This is obviously electricity. Okay, electricity. You know, electricity is exergy. Okay, electricity is exergy. How can I compare electricity with watt from electricity? How can I compare this with watt coming from fuel? Okay, because, well, I can have a heat flow in terms of watts, but it's different than electricity also in terms of watt. So the solution is simple. You only have to compare, you simply compare with the exergetic content of the fuel, or instead of using this number here, 997, which is the heat capacity or the heat supplied, you compare with the exergy supplied or the exergy content of the fuel. Okay, so we can make this graph. We can add liquid fuels here or here, I don't know. We can add liquid fuels, but when we do the energy calculation, we use exergy here. And that's the point. When you do this, that's the result. So all those batteries that were shown here in this previous slide will fall here in this region, okay? And liquid fuels will fall far beyond here, okay? So you see batteries, the numbers here, just to have a number. So it's 100, 200, 300, 400 watt hour per kilogram, okay? And so so here you have the order of magnitude. It's 10 to the second power, okay? In terms of massic density, let's say, like massic density and mass or volumetric density, something like this, okay? So batteries fall here and liquid fuels fall here, far beyond. So fuels can be 100 times, can do 100 times better than batteries in terms of how light they are, okay? Liquid fuels, I'm talking about liquid fuels, not gaseous fuels, okay? And liquid fuels can do 10 times better than batteries when volume is taken into account, okay? So this means that, well, the problem with using batteries in self-propelled vehicles is that compared to liquid fuels, it's going to be heavy and it's going to be cumbersome. It's going to be very large, okay? So that's a problem. And that's why the possibility of building hybrid cars is very, very, very interesting. Because hybrid cars actually combine two, let's say, the best qualities of a liquid fuel and of batteries, of not batteries, of electric motors. Okay, so a hybrid car. I'm going to talk about hybrid cars in another class. Okay, but roughly speaking, you have liquid fuel. Okay, which is the best way to store energy. Okay, you have internal combustion engine, okay, which is the only way that we have to transform liquid fuel to useful energy, to exergy, Okay, I use this. So here I have, let's say, a shaft power. I use it in a generator. Okay, electricity. I generate electricity here, and electricity drives a motor. Okay, and the motor drives the wheel of the car. Okay, so in this situation, you combine two winning technologies, let's say like this. The best way to store energy and the best driving technology. Because electric motors are very a lot better, do a lot better than internal combustion engines as a driving system, when you think of it as a driving system. Okay, so hybrid cars combine the two best possibilities. Okay, it's a liquid fuel. The energy comes from liquid fuel, but the way to transform the Exergy content of the fuel to kinetic energy of the car, the best way is with an electric motor. Okay, so you're combining two winning technologies. Okay, yeah, and you can do this calculation now. You understand. I hope you understand how this comparison is made, because you can now compare fuel in terms of its Exergy content. Okay, so this watt here is actually Exergy watts. Let's say it like this. Okay, yeah, that's it. I have only. Is there some doubt about today's class? No? Okay, I have just a quick reminder. Some people are asking me how to be warned when our classes are being transmitted online. Okay, what you have to do when you subscribe to my channel, you have to activate the warning system. For this, you have to click on this little bell here. Okay, so this is the way to get these automatic warnings when our classes are being transmitted live. Okay, another warning. Let me finish my presentation. Is that let me show here. You know, Tuesday, Wednesday, and today is the last day of Be Best in Campos do Jordão. Okay, I don't know if you've been there. I was there on Monday for a tutorial, and on Tuesday for the first day of the Congress. And what I wanted to say is that at least the tutorial that I coordinated. Let me get into the site. No, Be Best.
Excuse me, did you press the bell and just press the bell and mark something, or?
Yeah, let me show you. Let me go get to YouTube. Since I'm on YouTube,
Okay.
I'm going to try to subscribe to something. Oh, I'm going to get Khan Academy here. Okay, so where did I click? Khan Academy. Okay, so it's going to Khan Academy. So this is Khan's Academy. Let me maybe turn off the sound. So here, I have subscribed to this site, to this channel. Okay, and what you have to do here, in this little bell here, you see, get notified about every new video. So you click here and you can configure how much warnings and the types of warnings that you get from this specific channel. Okay, so that's what you have to do to get these automatic warnings. Okay, I have a few, for instance, here. Let's see, Jovem Pan Morning Show, for instance. So when they get live,
Na época
here,
era a notícia de
I get a
cabo
warning.
para
Actually,
comunicação
I don't want anymore,
era
so I
mais fino
press
que
here
fio
and
de
I'm not going to
cabelo,
get it. Okay?
centenas de vezes. E
Okay, and
tecido
what I
maluco
was
que
talking.
nem pegava
Okay,
sujeira.
so what I was telling
Algo
about
assim como
Be Best tutorial. Let's see, Be Best.
o avanço
Let
da
me get to the
tecnologia
site.
no agronegócio, que é um assunto importante para o Brasil. O Brasil, dos principais polos da produção agrícola do mundo. Está aqui a notícia de que 6 empresas assinaram contratos.
So Monday
menos 2 delas pretendem
we
lançar no meio do
offered
ano que
several
vem,
tutorial sessions,
novidades desenvolvidas
scientific
pela
tutorials.
rede de
This was on Monday. This was
para o agronegócio.
presented on Monday. So we have 4 tutorials,
Entre elas, por
1,
exemplo,
2, and I coordinated the 4th one, which is industrial production of biofuels, learning through experience. There were 3 tutorials.
Feitos de alimentos
Well, I don't see that.
Desprezados
I
e
don't see that.
hidrogel
Yeah,
que
here.
otimiza o uso de
Given by three speakers. Okay, I lecture this one. Professor David Caramonte from Italy, the second one, and Marcos Watanabe from CTBA, this one. Okay, those were the professors. And what I want to say is that I recorded all presentations, so mine was the first one is already online, and David Caramonte's is already, it's not yet online because I'm still editing the videos, okay? So if you want to watch this presentations, correspond to the first tutorial, I'm going to publish the videos online, okay? The first tutorial is ready because it was the first, okay? And today I intend to, today or tomorrow morning, I'm going to publish David Caramonte's tutorial, and I don't know when, Marcos Watanabe's tutorial I'm going to publish, okay? So you can see
no ano que vem também deverá chegar ao mercado o primeiro produto que usará filmes biodegradáveis, feitos de alimentos desenvolvidos pela Embrapa. São alimentos que seriam descartados.
Any doubt? No, channel, live stream.
Reaproveitados graças à atuação da nanotecnologia.
If there's no doubt, we are finished today. Thank you very much. And